When dealing with significant figures, it's really important to know how to deal with them in the context of calculations. And there are two categories really that we need to deal with this. So the multiplication and division category, which is where we're going to start, and then the addition and subtraction category. In multiplication and division, your answer can't have more precision than the least precise measurement. Or another way to say that, you can't have more significant figures in your answer than the measurement that has the fewest number of significant figures. So on this screen here, you see that if we're multiplying 5.02 times 89.665 times 0.10, in blue here is the calculator answer. All right, that's where our calculator will spit out to us. And in math class, that would be correct. But in science, where you're dealing with measurements, and measurements have a limited amount of precision, 5.02 has three significant figures. 89.665 has five significant figures. 0.10 has two significant figures. And so again, what that means is after the 0, we don't know what the digit is next. So once we get past the second digit here in our multiplication answer, we don't have a whole lot of confidence that that 0 is actually a 0. And so we're going to round this answer to two significant figures. Here's another example, this time with division. Four significant figures, 5.892, divided by something with three significant figures, 6.10, and we get 0.96590. That's the calculator answer. We have to round that to three significant figures because, again, after the third digit, we are not confident in the value that's in those places. So we round to three significant figures. Here's some other sample problems to walk through. I'm going to write above these the number of significant digits. So 1.01 has three significant figures. 0.12 has two significant figures. 53.51 has four significant figures. And then we're dividing by 96. And the 96 has two significant digits. So I'm going to go ahead and do that math. 1.01 times 0.12 times 53.51 divided by 96. And if I punch that into the calculator right, I get 0.06755,638. And that number may go on. That's just the number of digits that my calculator would display. And so I've got to round this to two significant figures, either based on the 96 or based on the 0.12. So when I do that, the proper way to report this answer is 0.068, and then whatever the units would be. Down below here we have 56.55, and that has four significant figures multiplied by 0.920, that has three significant figures, and then dividing that by 34.2585, and that has six significant figures. So our answer can only have three significant digits in it. So let me go ahead and punch this in, 56.55 times 0.920 divided by 34.2585. And my calculator spits out a very long number, 1.518, 63041, but we only want three significant figures. So the 1, the 5, and then the hundredths place. We're going to keep the hundredths place, but we have to look one more place to the thousandths place, and that tells me we're going to round this up to 1.52 as the final answer there. Now, when we have addition and subtraction, there are a couple ways to state this rule. In addition or subtraction, the result has the same number of decimal places as the quantity with the fewest decimal places. And so that's easy to apply when we have digits to the right of the decimal. I'll give an example later where we have measurements that don't have any digits to the right of the decimal. And so I would rephrase the rule at that point and say your answer can't be more precise than your least precise measurement. And so as we look at these down here, 5.74 plus 0.823 plus 2.651. Well, we can see here, we can kind of ask the question, what comes after the 4 in 5.74? We don't know. And if we don't know, then 3 plus 1 plus some number we don't know, the best we can say is that it's at least 4, but we're really not sure. Right? If that question mark in that first number is a 0, then yes, the answer is 4. But if that question mark is 1 or 2 or 3 or 4, well, that's going to affect the value in the thousandths place. We're going to add that number, those three numbers together just as we would normally, except we're going to end up rounding to 2 digits to the right of the decimal because of the 5.74. Same thing applies in subtraction. 4.8 has 1 digit to the right of the decimal. 3.965 has 3 digits to the right of the decimal. So that tells me that our answer can't have more digits to the right of the decimal than 4.8 does. So when we do the subtraction, we take a look at the digit after the 8, and that tells us whether we need to round or not, right? Whether that becomes 0.9 or remains 0.8. And because the 3 is 5 or less, then we're going to round that. We're going to keep the 0.8 and not round it up. So here's a sample problem to try. Right away, I'm looking at this and I'm seeing that 125.1 has 1 digit to the right of the decimal. And another way to say that is that that measurement is only precise to the tenths place. So my answer can't have greater precision than my least precise measurement. So when I punch this into my calculator and do the math, so 0.987 plus 125.1 minus 1.22, calculator spits out 124.867. But I know that I can only have 1 digit to the right of the decimal, so that's going to round to 124.9 as the final answer on that one. Here's one more. 3 digits to the right of the decimal in 0.765, 3 digits to the right of the decimal in the second number, 2 digits to the right of the decimal here. So I know my answer can only have 2 digits to the right of the decimal, or you might say it can only be precise to the hundredths place. So let me punch these into the calculator. 0.765 minus 3.449 minus 5.98. The calculator tells me negative 8.664. Well, I'm only keeping 2 digits to the right of the decimal, so negative 8.66 is the answer there. So now what if there aren't any digits to the right of the decimal? Let me just give you a real quick and simple problem here. Let's say we have 5,200 plus 136. Well, this brings up one of those ambiguous situations here. These zeros are placeholders, or we are assuming they are because there was no decimal written with that number. So if those zeros are placeholders, what that tells us then is that the 2 is the estimated digit. So that first number, 5,200, is only precise to the hundreds place. So when I add this, right, we get a 6, a 3, a 3, and a 5. that number is too precise. We need to round it so that it matches the precision of the least precise number. So the best answer we can come up with here is 5,300. And I know this is very different than what you do in math class, and it's going to be a little mind-bending. You're going to have to pause and make sure that you follow these rules every time, because your habit is to just give what your calculator says. Sometimes your math teacher will tell you to kind of arbitrarily round your answer, but there's nothing arbitrary about this. We have a set of rules that hopefully are logical, and that will become easier to follow as the year goes on. I hope this was helpful. Let me know in class if you have questions.